Section 2.8 is the mean value theorem, and we started talking about this last time. We talked about the fact that Rolle's theorem is just a specific example of the mean value theorem when the two endpoints are equal, and otherwise they're actually the same theorem. And so we talked about looking at deciding which of the two theorems apply based on the information we're given, and then we worked one example, and this was our example checking the hypothesis of Rolle's theorem and the mean value theorem, and then making some conclusions based off of that. So we're going to do another example, same directions, but my equation is f of x equals sine of x. And so what we're wanting to do is we're wanting to test the two hypotheses, or test the hypotheses of the two theorems, and see which theorem applies. So one of the hypotheses of the theorems is that we need to have something that's continuous. So is this continuous? And how do we know? Yeah, and not just trig function, but it's in particular sine and cosine functions, right? Because like tangent and cotangent, none of those have the continuity features. But sine and cosine are going to, because those two are the continuous ones that we talked about back in chapter 1. So it's continuous because it is sine of x. It's a sine function. What about the second condition? What was the second condition you have to check? Differentiable. Is this differentiable? Yes. And for the exact same reason, it's a sine function.
What is differential?
It means you can take its derivative. That's all differentiable means. You can take its derivative. And then the third condition. What is the third condition that we checked last time? Right, we tested the endpoints to see if they're the same. Okay? So our endpoints on this one are at 0 and pi halves. So what is the sine of 0?
0.
It is 0. And what is the sine of pi halves? That is 1. So they are not the same. So if they're not the same, it means it's not Rolle's theorem, right? This is the mean value theorem. So this is the mean value theorem because f of 0 does not equal f of pi halves. So let's take a look at the mean value theorem one more time. We haven't done that today. So let's look at it specifically and see what the difference is in what it says. So this says suppose f is continuous, which we said it was, differentiable, which we said it was. And then it says there exists a number c between a and b. So our a and our b are 0 and pi halves. Okay, so we're talking about the first quadrant of the circle that we're looking at here. Such that the derivative of c is equal to f of b minus f of a over b minus a. Now we have calculated f of b and we have calculated f of a. And we know what b and a are. So we can actually calculate the second side of this piece right here. We can calculate this piece of this equation without any calculus. This is just calculating a slope. Y values divided by x values. So over here on our problem, we're going to calculate that very same thing. We want to find out what is f of pi halves minus f of 0, and we don't necessarily have to do it in that order. We could have switched the order around. Divided by pi halves minus 0. Well, the numerator, we found those values. F of pi halves was 1, and f of 0 was 0. And then pi halves minus 0 on the bottom is pi halves. So right now this is equal to 1 over pi halves. I don't like fractions inside of fractions, so what do we do to get rid of that fact?
How do you know which one lies on top?
You always put y values on top.
Right, but
It's slope.
I didn't see that right. Sorry.
Okay.
How do you know to put the f by halves before the half?
It doesn't matter as long as the numerator and denominator match.
Oh.
So if I did f of 0 minus f of pi halves on top, as long as I did 0 minus pi halves on bottom, I'll get the same answer. Mm-hmm. Sure. Okay, what did you guys say we wanted to do with this? Right. And I think you mean reciprocal, right? So the reciprocal of pi halves is 2 over pi. So this ends up being 2 over pi. So my slope that I calculated is 2 divided by pi. So what the mean value theorem says is it says that there is going to be a location where my derivative at the value of c, the c value, is going to equal this 2 over pi halves value. Okay? Let me write one more step in here just to make it very clear. This is the f of pi halves minus f of 0 over pi halves minus 0. That's what we just calculated as 2 over pi. Now, on the left-hand side, I need to find a derivative. Agreed? So what is f prime of x for my function sine x? It's the cosine of x. So what would f prime of c be? Right, well, but except we're going to use c. So the cosine of c, which I don't particularly like c with sines and cosine functions, but
Where you lost me with the x. I believe you had f prime of x equals cosine.
our function, oops,
So the original function.
our original function was sine of x.
Oh, okay.
So I'm working, like over here on this page, I worked with the right-hand side of the equation. This is the right-hand side of that mean value theorem equation.
Oh,
And now I'm working with the left-hand side over here. So if I stick them together now, Chance, I have the left-hand side is going to be cosine, hang on, let me write it here, cosine of c. The right-hand side is the 2 over pi. All right, so how do I find the c value? Because that's my goal, is to figure out what c is.
Inverse cosine of 2.
Right. So if you take your calculator, you can do the inverse cosine of 2 over pi. And it's going to give you, if you're in radians, which you should be, we've been working with radians, this should give you a radian measure that looks like a funny decimal probably. What did it give you?
0.80689.
Okay, we'll go with 2 decimals. So the c value is 0.880. It's an angle measure. Okay, so this is an angle measure that's a little bit less than the angle measure of 1. Now, that's only part of the directions. The directions asked us to do one more thing. What did it ask us to do above? Yes, I think it asked it. Ah, yes it did. Illustrate it on a graph. So what does this look like on a graph? Well, you can graph sine of x between 0 and pi halves if you'd like. You probably know what it looks like, but if you aren't sure, you can go ahead and graph it. It looks like this, but without the left-hand side that I just drew in, right? So it's going to go from 0 up to 1 at pi halves. And it would go down after that, agreed? What we did when we found the right-hand side of the equation is we took the endpoints at 0 and at pi halves, sorry, that should say pi halves, and we connected them with a line. So what we found visually is that there's a location that's about at, well, it's at 0.88, right? So it's almost at the value of 1. So it's somewhere like right in here-ish. This is the 0.88 value that we found for C. And on the curve, right there, roughly, there is a slope that is identical to the slope or parallel to the line of this, the line, the tangent line, at the slope that we had on the right-hand side. And that's what the mean value theorem says we're able to do. That we're able to find a location that's got this average involved.
Is B like at the peak of the graph?
Well, it is on this particular graph, yes. Our graph, if we continue drawing, would come on down after this. Yeah, it wouldn't have to be on a graph, but it is on this graph. So let me, I mentioned this once before, but let me actually reiterate, I'll say it again, an application of this in real life, okay? When we talked about the intermediate value theorem, I told you that there was a connection between that and the mean value theorem, And I mentioned that there was a case, as in went to court and everything, where someone was never clocked going over the speed limit, but they were given a ticket for going over the speed limit. Do you guys remember telling you about this? Basically, what happened was that there were two. The policemen set up a trap, if you will, and they knew how far apart they were. They knew the distance apart they were. They knew the value for x, that is the denominator that's going on over in this particular formula. They knew this piece down here. They knew that they were a mile apart or 2 miles apart or whatever on the highway, okay? And so they knew how far in distance they were apart. And they could figure out then, based on how long it took the car to cross between car number 1, police car, and car number 2, police car, they could figure out the time that it took them. And by finding out the time and the distance that they had the numerator and the denominator for this, they could get an average speed. Make sense? If you know how long it took you to do something and you know how far you drove, you can get your average speed. That's what an average speed is. Well, if the average speed is over the speed limit, that means that somewhere in between those 2 points in time, car number 1 and car number 2, you had to be driving at least that average. And in fact, you had to been driving over that average if police car 1 and police car 2 both clocked you going at or under the speed limit. Does that make sense? That's what this is. The derivative is your speed right now. The right-hand side of this is your average speed. So we're saying that your speed right now has to equal your average speed sometime. At some point, that has to happen when you're looking at this particular sort of a case example. Okay? All right, we have a couple theorems here that we're going to take a look at. Theorem 8.2, and then we're going to have 8.3, I think, here right after it. Theorem 8.2 says if f is continuous on the interval a to b, differentiable on the interval a to b, so same conditions, right, as we had before. It says, and f of x equals 0 has 2 solutions between a and b. Then the derivative has to have at least 1 solution between a and b. And all this is pretty much Rolle's theorem. It's just saying that we don't have to worry about it actually being the end points that are equal to 0, equal to each other. So if you take a look, this is saying that if you had a graph, let me do it this way. If you have a graph and it's continuous and differentiable, so I'm going to just draw a curve. And it crosses the x-axis at 2 particular points. Well, if it crosses the x-axis twice, which is what this says, then at least one place between where it crosses and where it crosses the second time, it's going to have a slope of 0. It's going to have the horizontal tangent lines. Now, the way that I drew it, I've got 3 of them. Agreed? I have 3 peaks and valleys, so I've got this location, and this location, roughly speaking, where I have horizontal tangent lines. But at the very least, I've got to have one location where this would happen. And can you picture it? Like if I had the one location, it'd look like parabola, right? And so it's saying that it doesn't necessarily have to be that the A and the B are these particular places where they cross. And it doesn't necessarily have to be that A and B are the same. Their Y values are the same. So if we did this particular point and we did this particular point, right? So if the A value was right here where I did the first purple and a B value is over here, all of this would still be true because we could sort of like condense the viewing window that we're looking at, and we could start with the x-intercept over here and the x-intercept over here could be our ending point, and then we'd be back in the case of Rolle's theorem. That's all it's saying, is that we can kind of collapse what we're looking at and only look at the points where we have x-intercepts to look at this. Okay? Let's take a look at one more. Theorem 8.3 says, for any integers n greater than 0, f is continuous on the interval, differentiable on the interval, and it says that our function f of x equals 0 has n solutions. So not 2 anymore. It's not 2 places where it crosses the x-axis. It has n places where it crosses the x-axis. If that's the case, then f prime of x equals 0 has at least n minus 1 solutions. At least. So the picture I just drew you a moment ago was the case where it only crossed the x-axis twice. But let's imagine that it crosses multiple times. And let's let it go down from here. The way that I've drawn it is the minimum case that it's referring to. I'll draw you another possibility in a moment. So if you take a look at the one that I drew, how many times does it cross the x-axis? 4 times. So according to this theorem, there should be 3 locations at least where it has slopes of 0. 1, 2, 3. Does it? Yep. Could it have more? Yeah, it could. We could have had it drawn something like this. Maybe, in fact, the graph I did before would have worked. Say it does this. It crosses the x-axis on this one 3 times, agreed? Which means it has a minimum of 2 places where the slope is 0. But this one has more. 1, 2, 3, 4. It has 4 locations where the slope is 0. So this theorem is a minimum case theorem. It does not tell you how many it has. It tells you at least how many it has. Any questions on the descriptions of the theorems first? Okay, we're going to do an example with it then. I have 2. All right, first example. It says to prove that x to the 4th plus 6x squared minus 1 equals 0 has exactly 2 solutions. So both of these theorems above, they're really the same theorem. Let me just say that first. 8.2 and 8.3 are the same thing. 8.2 is just sort of a condensed case of 8.3. It's the case when n equals to 2. That's the only difference in them, okay? So what we want to do is we want to be able to take a look at an equation and make sure that we have all the conditions set up in 8.2 and 8.3. So there are 2 conditions, and they're the same conditions we had for mean value theorem and Rolle's theorem. What are the conditions first? And differentiable. So as you're working in this section, I know it doesn't feel like you're really doing a lot by stating it, but you do have to make sure that you really do have something that's continuous and differentiable. So is this going to be continuous and differentiable? Yeah, why? Yeah, because it's a polynomial.
Okay, and I don't understand that definition because of what if you had a polynomial over a polynomial? Is it no longer classified as a polynomial?
No, it wouldn't be. That would be a rational function.
Oh.
Yeah, the only way you have a polynomial has whole number exponents. So they could be not even whole number, integer exponents. I'm going to start again. You have exponents. The exponents have to be whole numbers. They can't be negatives. They can't be fractions or decimals. And if you had something in a denominator, it would have the effect, basically, of having some kind of a fractional component to it. The other problem, if you had something in the denominator, is that you have a potential place anyway. It wouldn't have to, but you have a potential place where you'd have an asymptote or a whole, right?
Yeah.
Now, there are cases when you wouldn't, depending on what functions you were looking at. But rational functions do not have the property that they're continuous everywhere, generally speaking. Yeah. Okay, so we've got something that's continuous in the differentiable. All right, so the next thing that we're going to do is I want you to take a look at the graph, okay? So I want you to put in this piece right here, not the equals 0 part, but this piece right here into y1 in your calculator. Now, unfortunately, this x to the 4th plus 6x squared minus 1, it does not factor, or at least not with any sort of typical factoring theorems that you're aware of, or anything like that. Techniques would be a phrase better. Techniques. I can't just set this up and factor it very nice. So deciding whether it has 2 solutions or whatever, that's a little trickier than taking a look at this from the other direction. So we're just going to take a look at the graph first and see or confirm to ourselves that it seems reasonable that it has 2 solutions before we go any further, okay? This won't prove it, but at least it's going to seem reasonable that it does. Do you guys follow me so far? Okay, so take a look. What's the graph look like?
The skinny parabola.
It looks like a skinny parabola. Does it look like it crosses the x-axis twice? Yeah. So the graph that I've drawn right here says that it looks, or that I've shaded it here on my paper, it looks something like this. And I have mine set up when I did it as a negative 10 to 10 window. So does your graph look something like this? Yeah? Okay, so what I want you to write down or note to yourself is that you didn't prove anything. All you did is confirm that this seems like a reasonable statement. Okay? So I'm going to write this here too. This looks to So this looks like it has two solutions. We'll say it that way. You could do things in your calculator. You can do some tracing features and stuff like that to approximate those solutions and so forth. That's not really what we're trying to do here, because what the directions actually said is that it wants us to prove it. Do you guys see that okay? It wants us to prove something's happening. So what we're going to do is we're going to actually make a couple of comments. First, we're going to make a comment that says, I can for sure tell you it has to have at least this many. And then I'm going to say, for sure I can tell you I can't have more. So our game plan, if you will, and I'm writing this down not because I expect you to write down game plan on your paper, but because as you're looking at this, I want you to look back at this and remember why we did what we did. This really confused my students last semester, so I want to hit this a little bit stronger than this time around. Is we're going to show it must have at least two solutions. And we're also going to show it cannot have more than two solutions. Right? If it has to have at least two and it can't have more than two, then we must have two. And that's how this directions actually said. It said it wants us to find or to show that it has exactly two. So we're going to show it can't be less and we're going to show it can't be more.
Whatever you
Yes,
said,
Chance.
that graph looks like it would have two solutions.
Yes.
Like I see the one at the bottom, right? But
Okay.
I'm not seeing it.
Equal to 0 means places where it crosses the x-axis.
Oh, okay.
Yeah, not slopes of 0. We're not talking about where it has a slope of 0 right now. We'll get to the slope issue in a minute, though. That's actually part of what we're going to have a discussion about here. But right now we're just saying we think it reasonably has two places where it crosses the x-axis. Okay? And we're going to use theorems 8.2 and 8.3 in conjunction to do that. Here's the first thing, though, all right? We're going to do something with a little bit of algebra to show the at least two solutions. Okay? What I want you to take a look at is I want you to take a look at finding the function value at three locations. In particular, one of them is going to be f of 0 because it's easy to calculate. I like plugging 0 into things. The other two are going to be on either side, and I'm going to choose f of negative 2 and f of 2. There's nothing really special about them. You could choose something bigger if you want, f of 3 and negative 3, whatever. If you've already put this in your calculator, I think everybody did, you can go into your table and just plug these numbers in. So if you go into your table, you can put in x equals negative 2, x equals 0, and x equals positive 2. So f equals negative 2, what does that give you? 39, good. How about at f equals 0? And at f equals to 2? Did you get 39 as well? All right. The fact that this was positive and then becomes negative means by the intermediate value theorem, it's back in chapter 1, it crosses the x-axis. i.e. f of x, our function equals 0, which is what we're trying to state. And the fact that it went from negative to positive tells us it did it again. The intermediate value theorem tells us that if you're below the x-axis and then you're above the x-axis and it was something that was continuous, which this is, somewhere between there it had to cross. So we know that it has to have at least two solutions. So this tells us there are at least two solutions, i.e. two places where x equals sorry, not x, f of x equals 0. That's what this tells us. There has to be two places, at least, where this happens. Here's the problem with for sure knowing right now that it's only 2. You graphed it in your calculator, agreed? And when you did it, you had a certain window showing up. What happens if your window is insufficient?
Zoom out.
You could zoom out, but how do you know how far to zoom out to make sure that it's never going to curve back down and cross again?
Zoom all the way out.
All the way out. Just keep zooming. So do you kind of see the inherent problem with assuming that the picture you're looking at is the whole picture? I mean, that's kind of the problem here, is that your calculator has a limited capability to show you things. And it's sort of based on what you tell it to do. But it is limited in its abilities. So our proving this is independent of the technology being sufficient for what we need. That's what we're doing. We're saying, without the technology, I can still show you that this is going to work. And I'm not sort of waving my hands at saying it works. I'm not sort of just assuming that the picture I'm getting is enough. So right now we've done the first thing on this list. We were supposed to show it has at least 2 solutions. We did that. The next thing is I need to show that it has no more than 2 solutions. Okay? So how do we do that? Well, what we're going to do is we're going to take the derivative. So this is our game plan, part 2 of our game plan. We're going to take the derivative of our function, and we're going to find out where it equals to 0. So let's do that first. What is the derivative of the function that we started with, of x to the 4th plus 6x squared minus 1?
X to the 3rd plus 4x.
So after your derivative quiz, that was a clean, simple, easy one, right? Yes. And this is equal to 0. So let's find out where in the world this actually has zeros. That is, let's factor it. So how can we factor this? Factor out 4x. That sounds like a good plan. That leaves me with x squared plus 3, right? What do I do next? Right. You set each part equal to 0. How about this first one? Where does x equal 0? At x equal to 0. What happens over here at x squared plus 3?
Using bad numbers.
Oh, I don't think so. What happens?
Square root of a negative number.
So what happens when you have a square root of a negative number?
Yes.
It's imaginary. What number system are we working in?
Real one.
The real number system. So when I get imaginary solutions, it means it's not present in the real number system. Make sense? So this one has no solution. So this one can't happen in the real number system. The real number system is represented by a capital R with 2 lines on the left. So there is no solution to this in the real numbers. Agreed? X squared can't equal negative 3. It doesn't work. Okay? So we only have one location. There's only one value where f prime of x equals 0. So let's go back and take a look at what theorem 8.2 and or 8.3 can tell us about that. 8.2 actually works just fine on this one since we have a small number. 8.2 said that if the original equation we were dealing with had 2 solutions, then we would have at least one solution in our value system, right? We found something that we have a derivative equal to 0, and it's exactly one derivative equal to 0, right? So if we go back up into this sort of reasoning right here, what we're actually being told is that we had to have had a minimum of 2 solutions. We can't have had 3. Maximum of 2 solutions. Sorry, not minimum. Maximum. We can't have had 3. So let me write this down in a little bit different order so that we can follow it going forward instead. F of x cannot have 3 or more x-intercepts. And you might say, why? Because if it did, we'd have 2 or more, I'll put that in parentheses because that's still an option, or more places where the derivative equals 0. Do we have 2 or more places where the derivative equals 0? We only have 1, right? We only have 1 place where the derivative equals 0.
Because the derivative isn't, like, that's what gives us our whole picture, but our graph can't, because the derivative will show us every value that.
The derivative shows us every place where it might change direction in particular, right? Or even flatten out, but for the most part it's a change direction issue. So the derivative is basically telling us there's only 1 place on my graph where it changes direction. And if that's the case, then there isn't anything out on the extremities of this graph where it could change direction again. So you're exactly right, Will. That's what the derivative is giving us the information on that we didn't have before. What's going on the edges of the graph? Well, I don't know for sure, but I do know it's not turning around and going back down. And that was my concern, is that there might be a place where it might happen to do that. So we don't have that case happening. So let's see, f of x cannot have 3 or more intercepts because if it did, we'd have 2 or more places where the derivative equals 0. And we only have 1 place where the derivative is equal to 0. So we have, at most, 2 places where f of x equals 0. So we showed, first of all, that we have at least 2 solutions. We showed, second of all, that we have at most 2 solutions. So we have exactly 2 solutions. I am really not using my screen very well today. Sorry about this. I'm all over the place.
So if the f prime did come out as having 2 x equals stuff, we would have more than 2 plus.
Yeah. Hang on, and I'll answer that question too after I finish writing this down. So we know we have at least 2 solutions and at most 2 solutions, hence we must have exactly 2 solutions. All right, so if we had found the derivative chance, like you were saying, like we did over here, and instead of it saying x squared minus 3 is not equal to 0, let's say it said x squared, I'm sorry, instead of saying plus, let's say it said minus, so we actually got a solution. What that would be telling us, if we had found 3 solutions, which is what we would do if we actually could have set that equal to 0 and got a solution, we've had 3 solutions, is that we would have had to have had at least 4, or we have at most 4 places where it had the possibility of crossing the x-axis, and we would have been stuck. So this one doesn't have that feature. I think I have one more that's a little bit different question. Are you guys ready? Yes. Yeah, because you're going to have to show that it really doesn't have more than 2 and it really doesn't have less than 2. And so do you have to write out everything that I wrote out? Not necessarily, but you're going to have to show those 2 pieces, and your conclusion is going to have something to the effect of what I wrote here in blue, where I said at least 2 didn't, we know we have at least 2. We know we have at most 2, which means we have exactly 2. So you're going to have to do a little bit of writing in order to make that make sense. So yes. Okay. All right, a little bit different question. This question says, determine where the function is increasing, decreasing, or neither. And our function is actually very similar to the function we just looked at. A little bit different, but very similar. It's a power 4. It's x to the 4th plus 2x squared plus 1. So if we're wanting to know where our function is increasing or decreasing, now this goes way back to something that we did back in section 1, I think, of this chapter. Do you remember when you drew some graphs and you had to write down details of how the graphs were changing in order to draw the derivative graphs? Do you guys know what I'm talking about?
Is that what they're supposed to say where?
No, it's supposed to say whether, so it may be a where, but yeah. It could be increasing, decreasing, or neither. So, oh, I see what you're saying.
See what I'm saying?
Yeah, we'll say where. I'm not sure how your book words it. Yeah, it may be that it's always increasing or always decreasing, but that would still work with the word where. So let's put where. I think that makes it a little bit more general. Yeah. Okay, do you guys remember drawing graphs? Back at the section 2.1? I'd review those if I were you, because that might show up on a test. Just saying. Something we haven't done in a long time, right? I mean, really, it's been like 3 weeks since we've drawn those, I think. So do you remember how it was related when a graph was increasing, how it relates to the derivative graph and so forth? Do you remember how those are related? What could you tell me about slopes when graphs are increasing? Slopes are positive. And what happens when a graph is decreasing? Slopes are negative. So if we're finding out information about where something's increasing and decreasing, it's a lot easier to find out where something's positive or negative. Agreed? That's a much easier question to answer, is when something's plus or when it's minus. It's a lot more difficult to talk about where it's increasing and decreasing because I'd actually have to compare 2 points to decide, is it going higher as I move or is it going lower? I'd have to actually have 2 points to make a comparison. So this idea of being increasing or decreasing is that if a graph, like you said, is if f of x is increasing, then the derivative is positive. And if f of x is decreasing, then the derivative is negative. Those are important pieces of information, and I believe some of your true-false stuff on your quiz or on your review will actually ask some questions about this idea. Okay? So if I'm wanting to know about increasing, decreasing, we can find out information about the derivative where it's positive and negative. So what in the world do we get when we take the derivative of our function?
4x cubed plus 4x.
Look good? Now think again with me. If a graph has some places where it's increasing and a graph has some places where it's decreasing, then that also means that at some point it does this, right? Where it's increasing, it stops increasing, and it starts decreasing. And what do we say about this particular place in terms of its slope?
0.
The slope is 0. Now, it could be the way I actually drew it, that it also is undefined. It could have a sharp turn. This one won't. Do you know why? It's a polynomial. Polynomials are always smooth, so they don't have any sharp turns. So we don't have to worry about that. But we are going to be worried about where in the world this is actually equal to 0. Now, we did something similar to this in the last problem. So what did we do next when we're trying to find out where this is equal to 0? How? We are going to solve, but how? Factoring. So what are we going to factor out? 4x actually works. Which leaves me with x squared. Well, 4x will work because they both have a 4 and an x in them. 2x would be fine too. It wouldn't hurt anything, but what's going to be left after this? Am I done? Plus 1, right? You got to remember that factoring is like division. When I take the 4x out of the 4x that's already there, I'm still left with the number 1. All right. Noah told me on the last one I set this equal to 0, so I think I still do the same, don't I? Yep. So the first one equals 0 when x equals 0, and the second one doesn't work. It's the same problem we had before, right? All right, so here's what we do next. The next thing we do is we set up a number line, and there's more than one way to do this. I think a visual is a little bit helpful. And so I do a number line with the number where I just got is set equal to 0. And what I want to do is I want to test a value on either side of this, and it doesn't matter what test value I use. So if I pick a different point than you, that's fine. And I want to test it into the derivative. So I want to find f prime of something that's smaller than 0, so somebody give me a number. Negative 1. And I want to find f prime of something that's bigger than 0. 1. So I want you to take the numbers negative 1 and or 1, one at a time, and plug them into the derivative. F prime of x equals 4x cubed plus 4x. What I care about is whether I get a positive or I get a negative. I don't care about the number I get. All I care is whether the number is positive or negative. So when we plug in negative 1, what do we get? So we get a negative. When I plug in positive 1, what do I get?
Positive.
I get a positive. So what we just found out is that the derivative, this is all information about the derivative, is negative before 0 and it's positive after 0. So I didn't write this out on the slide already, but I think I probably should because I'm getting some weird looks from you guys.
Where did you get the 8? That's what I'm trying to think.
Where did you get 8?
Yeah, you plug in -1 in the original equation, right?
No, we're into the derivative. That's why this says f
Oh,
prime.
into the,
F prime. So here's the deal. If f prime of x is negative, then f of x is doing what? Decreasing. And if f prime of x is positive, then f of x is doing what? It's increasing. Now, it's a little bit trickier to write down the last one. If f prime of x is equal to 0, what could be happening? Yeah, it's leveling off. It's kind of flat, right? Say again for me, Noah. If there was a corner, we wouldn't get f prime of x equal to 0. We'd get it does not exist. It could be a max or a min. Does it have to be? No, it wouldn't have to be, but it could be a max or a min. That's a possibility. So there's options of what could be happening if it's actually equal to 0. But taking a look back at our picture, whoops, over here, this said it was negative. So what does that mean is happening? Yeah, it means the original graph right here. So from negative infinity to 0, the derivative was negative, which means f of x is decreasing. And from 0 to infinity, that is over here, the derivative was positive, which means f of x is increasing. Here's the cool thing about this. You proved all that without graphing it, agreed? I want you to graph it now and make sure that your graph matches what you think you found analytically, algebraically, with calculus here. Make sure it matches. What picture do you get? It won't be a surprise. It's not a shocking picture or anything. What do you get? What's it look like, basically? What's it look like?
Skinny parabola.
Yeah, it looks like a parabola. It actually doesn't cross the x-axis this time, does it, Will? It's actually all above the x-axis, so it looks like this. What we just wrote down is that before x equals 0, which is the y-axis, it's decreasing. Is it?
Yep.
Yep. And we wrote down that after x equals 0, after the y-axis, it's increasing. Is it? Yeah. So the graph matches what we just confirmed algebraically. Okay. Everybody good? Yes. No. On the homework, you have to set the derivative equal to 0, and you have to test the points. Whether you draw the picture for the points with the number line, I don't care. Yeah. So if you did everything we did here, and you didn't have this piece right here, if this was missing, that would be fine. You could still make the same claim without that picture piece of it. Yeah.
Do you need to draw a graph or no?
You wouldn't have to draw a graph. The only reason I suggested drawing the graph and we just sketched it over here was so that you could confirm your answer.
Okay. The points that you test just have to be on either side. They don't have to be differing, positive or negative.
Right. Either side of whatever the x value is you're working on. Our x value happened to be 0, but let's say you had an x value that was 7. Well, it needs to do something before 7 and something after 7. So maybe you pick 5 and 8. Maybe you pick 0 and 10. I don't know. I mean, you can pick anything. Just it has to be on either side of the x values.
Okay.
And if you have 3 x, more than one x value, say you had 2 x values, you have to test every piece in between. Right? So if you had x equals 2 and x equals 7, you need to test something before 2, between 2 and 7, and after 7. You have to test all pieces of the picture. I guess that's partly why I draw pictures, is so that I make sure that I test all the pieces that I need to do, and I can see a picture of it. Any other questions on this? Okay.